So far in this course, we've spent most of our time talking about linear functions and linear models. However, there are lots of kinds of functions that are not linear. So at this point, we're going to take a little bit of an aside, and we'll talk about one common kind of nonlinear function. We're going to talk about exponential functions and exponential models. With that in mind, we need to take a quick review of just what exponents mean. So we have here an exponential expression, where here the 3 is the exponent. The 2 we can call the base. And when we want to evaluate an expression that involves an exponent, we need to work out, what is 2 to the third? And that means 3 copies of the number 3. And that means 3 copies of the number 2 multiplied by itself. So 2 to the third means 2 times 2 times 2. We can multiply that out by hand, right? 2 times 2 is 4. And then 4 times 2 is 8. We can also do that on the calculator. We can do 2 times 2 times 2. Or we can just directly evaluate 2 to the power 3. Notice the exponent key is this little upward arrow that's right up above the division key. So 2 to the third is 8. 3 to the fourth, that's 3 times 3 times 3 times 3. And then 3 times 3 is 9, so we have 9 times 9 is 81. And again, on the calculator, 3 to the fourth is 81. Negative 5 to the second power, right, that means negative 5 times negative 5. Negative times a negative is positive. 5 times 5 is 25. So negative 5 to the second power works out to positive 25. On the calculator, negative 5 to the second power works out to 25. And notice we need those parentheses. Without the parentheses there, that means take 5 to the second power and then make the result negative. Now, 6 to the 0 is tricky, right? So we take no copies of 6. The way that we define this is to say, well, if we have the 0th power, we don't do any multiplying at all. So the number that does no multiplying at all is just 1. And again on the calculator, 6 to the power 0 comes out to 1. Anything to the power of 0 just comes out to 1. Now, our goal with exponential functions is to write our variable in the exponent position. But variables can take on any values. In particular, variables can take on negative number values. So before we can write an exponential function where we write a variable in the place of the exponent, we need to know how we can understand an exponent that isn't a whole number, right? 2 to the third represents 3 copies of the number 2, but I don't know how to take like negative 2 copies of the number 2. So let's use patterns in our whole number powers. Right, so 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, those are easy. Right, 2 to the first, that's just one copy of the number 2, so that's 2. 2 to the second, that's 2 times 2 is 4. 2 to the third, that's 2 times 2 times 2, so that'll be 8. 2 to the fourth, that's 2 times 2 times 2 times 2, that's 16. And notice that every time our exponent increases, we multiply by 2. So 2 to the 0, that's something we know. But also, we're looking for the number that when we multiply it by 2, we get 2. So that must be 1. These negative powers, right, we haven't seen these before, but they should follow the same pattern. So 2 to the negative 1 must be the number that when I multiply it by 2, I get 1. Well, that's going to be 1 divided by 2 is a half. And then 2 to the negative 2, that must be the number that when I multiply it by 2, I get a half. So that's going to be a half divided by 2, which works out to be a fourth. So the pattern that we see, first of all, increasing the exponent by 1 multiplies the result by 2. And the other thing that we notice is that 2 to the negative 1 is the same as 1 over 2 to the first power. Right? We see those two numbers are reciprocals of each other. And similarly, we see that 2 to the negative 2, that's the same as 1 over 2 to the second power. In general, what the negative sign on the exponent tells us is to take the reciprocal. The negative sign on the exponent tells us to take the reciprocal and make the base, or make the exponent positive. And that's the informal way of stating what this next box is stating more formally. So if we have a negative exponent, if we have a to the negative n, that's the same as 1 over a to the n. Or if we have 1 over a negative power, that's the same as just the positive power. Or if we have a negative fraction, or a negative power of a fraction, That's just the positive power of the reciprocal of that fraction. So let's see a couple of examples of working with this definition of negative exponents. So I have 2 to the negative 3. By definition, that's 1 over 2 to the third, which is 1 over 2 times 2 times 2. That's 1/8. And again, we see we can confirm this on the calculator. If I take 2 to the power negative 3, well, my calculator automatically gives me a decimal. But if I press Math, pick the first option, I can convert that to a fraction. And indeed, that's the same 1/8 that I just got by hand. 5 to the negative 1, that's 1 over 5 to the positive 1. So that's just 1/5. Again, on the calculator, I take 5 to the power negative 1, and then I can say convert that to a fraction just right away. And indeed, we get that 1/5. Negative 3 to the negative 4, the negative exponent tells us to take the reciprocal. But then that negative sign on the 3 is just making that a negative number. So we have 1 over negative 3 times another negative 3 times another negative 3 times another negative 3. So negative times negative is positive, times another negative is negative, times another negative is positive. This will be 1 over positive 84. Not 84, 81. And again, if we say negative 3 to the power negative 4, give our answer as a fraction. That's exactly what the calculator gives us. Finally, now this last one's a little bit different because it's a fraction. Right? We have 2/3 to the negative 4. We take the reciprocal, 3/2 to the positive 4. Right? So that'll be 3/2 times another 3/2 times another 3/2 times another 3/2. Multiplying the numerator gives us 81. Multiplying the denominators gives us 16. Again on the calculator, parentheses, and we'll actually use fraction entry here. So 2/3 to the power negative 4. And because I used fraction entry, it automatically gives me the result as a fraction. And I get 81/16. So, however I go about this, the negative exponent means take the reciprocal, and the calculator will correctly give me the result of plugging in a negative exponent. Okay, so now that we know what it means to write a large variety of numbers in the exponent, let's think about writing a variable there. So we've spent a bunch of time talking about linear functions, which can be written in the form y equals mx plus b, or in function notation, f of x is mx plus b. Now we're talking about functions that are not linear. They won't be written in this form, but they're written in a kind of parallel form. The functions we're going to talk about right now are exponential functions, and they can be written in the form y equals some starting value times some other number to the power x. And again, we can go into function notation as well. We can write f of x for function notation, or we can just write y and think of the output as another variable. And there are a couple of rules. First off, we're going to say that this number that we're multiplying by is not 0. Well, that makes sense, right? If we just multiply the whole thing by 0, that's a pretty boring function, right? It's just the function that's always 0. We're not going to say that that's exponential. Second, we're going to say that this number b, right, that's the number we're raising to the power x. That number has to be a positive number. And the reason that it has to be positive has to do with some weird behavior with negative numbers if we let the exponent be a fraction. So it has to be positive. And also, it's not 1. Why is it not 1? Well, 1 to any power is just 1. So again, that becomes a very boring function. So we only have an exponential function when we have, it's going to turn out that this number a is a starting value, and this number b is something that we multiply by again and again. So we don't start at 0, and then we multiply by something that's not 1 over and over again. We have an exponential function. So this next example shows us the kind of situation in which exponential functions show up. We have bacteria in a petri dish and they're multiplying. We start with 3 bacteria. So we start with the number of bacteria being 3. And then every time 1 hour passes, the number of bacteria is multiplied by 2. So when no hours have passed, there are 3 bacteria. After 1 hour passes, now there are 6. Another hour passes, and now there are 12. Another hour, and now there are 24. Another hour, and now there are 48. So here I'm writing, I multiply by 2, and now there are 48. All right, so the pattern is when the input increases by 1, the output doesn't increase by a constant amount, but is multiplied by a constant amount. Is multiplied by 2. When the input increases by 1, the output is multiplied by 2. And we can draw a graph of this. Right? So when when t is 0, n is 3, so we have a point here. When t is 1, n is 6. When t is 2, n is 12. When t is 3, n is 24. And then when t is 4, n is 48, and that's off the graph. And what we see is that these points don't all lie along a straight line, right? If I try to draw a straight line that goes through 2 of these points, it's going to miss the other points. I can't draw a straight line that passes through all of these points. Instead, what I have to draw is a curve. And we'll see that this curve is going upward more quickly as time passes. So it's going to pass through these dots, and then it'll disappear off the top of the graph before it gets to the next grid line to the right. And what we'll see in a little while is that as we go off to the left, it just gets really, really close to zero. Of course, in this application, presumably before we start, there are no bacteria in the tray at all, so anything to the left of zero is not especially interesting. The way we describe this function is by writing n of t, so the number of bacteria as a function of t, is equal to 3, that's the starting value, times, well, every time t increases by 1, we multiply by another copy of 2. So this is the number that we multiply by each time t goes up by 1. Remember, when we were talking about linear equations, the intercept was the starting value, and then the slope was what we added to the output each time the input went up by 1. Well, now here, the first number that we're multiplying by is the starting value, and then the base for the exponent, which we'll call the base multiplier, or just the multiplier, is what we multiply by each time the input increases by 1. And we call that the base multiplier property. If we have an exponential function, y equals a times b to the x, if the value of x increases by 1, then the value of y is multiplied by b. So we can see this in a table of values. Here we have another exponential function, g of x equals 4 times 1/2 to the x. Now I'm not going to actually start at -3 here. Right, I'm going to start at x equals 0 and say that g of 0 is 4 times 1/2 to the 0. 1/2 to the 0 is just 1. So this is 4 times 1. G of 0 equals 1. Now the rule tells us that every time we go down a row in this table, we should be multiplying by 1/2. And what I'm going to do here is just go through and put all of these into my calculator. Right? So g of -3, that's going to be 4 times 1/2 to the -3. 4 times 1/2 to the -3. That worked out to 32. G of -2, that's going to be 4 times 1/2 to the negative 2. That's 16. G of negative 1, that's going to be 4 times a half to the negative 1. That's going to be 8. Sorry, 4 times 1 is 4. Now, G of 1, that's going to be 4 times a half to the first power. That's 2. G of 2, that's going to be 4 times a half to the second power. That's just 1. And G of 3, that's going to be 4 times a half to the third power. And that works out to be a half. And we hope that the pattern will be each time x increases by 1, g of x is multiplied by a half. Now, if you think a little bit and think multiplying by a half, that's just dividing by 2. And you notice that at each step, our value is divided by 2. That can be easy to see. Otherwise, we'll take 32 times a half. Really does give us 16. And then we'll multiply that answer by a half. Gives us 8. Do that again, gives us 4, then 2, then 1, then a half. So that really is what's happening, right? Every time my x value goes up by 1, my output is multiplied by a half. And we can graph this, right? X is negative 3, y is 32. X is negative 2, y is 16. X is 1, y is 8. X is 0, y is 4. X is 1, y is 2. X is 2, y is 1. When x is 3, y is a half, we'll just kind of eyeball that. And then we can fill in the rest of this curve. And again, not a straight line. This is what's called an exponential curve. And you'll notice that in this example, we got an exponential curve that was somehow decreasing. In the previous example, we got a similar shape that was somehow increasing. What made the difference? Well, what made the difference was what number we're repeatedly multiplying by. In our first example, every time the input increased, the output was multiplied by 2. And in the second, every time the input increased, the output was multiplied by a half. Oh, this is a typo. This should say if b is greater than 1. So if we have our exponential function in base multiplier form, a number times another number to the x power, then if the number we repeatedly multiply by, if our b, our multiplier, is greater than 1, every time we multiply by something greater than 1, the output is bigger. And so we get an exponential curve that looks like this, and we describe that as exponential growth. On the other hand, if b is a fraction smaller than 1, and remember b is required to be positive, so if b is between 0 and 1, every time we multiply by something smaller than 1, the result gets smaller and smaller. So we have this decreasing exponential curve, and we describe that as exponential decay. We use the word decay to describe an exponential decrease. Notice also that these exponential functions are going to have no x-intercept. Why not? Well, in the exponential growth, as we go off to the left, right, we're dividing by some positive number, but no amount of dividing by something is going to get us to 0. In exponential decay, as we go off to the right, we're repeatedly multiplying by some small fraction. No amount of multiplying by something that's not 0 is ever going to get us to 0. So because our y values, our outputs, can never get to 0, our exponential curves are never going to have an x-axis. Excuse me, are never going to have an x-intercept. Okay, we can do all of the same things with exponential curves that we could with straight lines, because we have this nice form for the equation. So here we have a graph of an exponential function, right? And looking at this graph, we can see some kind of nice points on here. The y-intercept, where we cross the y-axis, we can read off, that's 0, 1. F of 1, right, we're looking for the y-coordinate when the x-coordinate is 1. We see that this is the point 1, 2. So f of 1 is 2. If we say f of what equals 4, we're looking for the x-coordinate when the y-coordinate is 4. We see that this is the point 2, 4. And so f of 2 is 4. Another way to think about this is to think of the pairs of values we see, right? 0, 1, 1, 2, 2, 4. We can think of that as an input-output table. So when x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. Each row in the table, our x is increasing by 1, and our y is being multiplied by 2. Okay, so we're going to write y equals a times b to the x, where a is the starting value, and b is the multiplier. So in the table, when x is 0, y is 1. So this is the number a. Each time x increases by 1, y is multiplied by 2. So this is the number b. Our function is f of x equals 1 times 2 to the power x. Or since multiplying by 1 doesn't do anything, we can just write 2 to the power x. So the graph that we were just given, we can figure out is the graph of 1 times 2 to the x, or just 2 to the x, by looking at the nice points we can see, constructing a table, and seeing what our base, our starting value, and our multiplier are. In these next couple of examples, we're not given a graph, we're just given the table. And based on the table, well, so in this first example, we're given the starting value. So we know A. And then in each row of the table, our input is increasing by 1. And let's see what we're multiplying our output by. To see what we're multiplying by, of course, we just do division. So here we'll do 18 divided by 6. And we can do that on the calculator if we need to. 18 divided by 6 is 3. So in this first row, we're multiplying by 3. Let's check if it's the same in every other row. All right, so we'll check 18 times 3. Is that 54? Yeah, it is. Times 3 again. That is indeed 162. So every time we go down a row, we're multiplying by 3. Our function is, our value A is 6. And then our multiplier is 3. And we have 3 raised to the x power. And we can confirm, we take 6 times 3 to the third power. So now I'm just plugging in x equals 3. I should get the last row of the table. I really do get 162. So when I plug in x equals 3, I really get the last row of the table. That tells me my function is correct. Okay, next table. Again, we see a row where x is 0. So our number A is 100. Next, every time we go down a row, what do we multiply by? Right, so we take the next row divided by the current row. So 50 divided by 100, that's 0.5, or I could make it a fraction, that's 1/2. So 100 times 1/2 is 50. We should check that we continue multiplying by 1/2. So 50 times 1/2 really does give us 25. And then times 1/2 again. Well, that gave us a fraction. Make that a decimal, that's the same 12.5 that we see in the table. So we really are multiplying by 1/2 every time. Our function is our starting value times our multiplier to the power x. Okay, one more table like this. We start at 0, So here's our a value. To figure out our multiplier, we'll take the second row divided by the first row, and we get 2.5. And for the sake of argument, this time I'll leave this as a decimal. If you have a nice decimal, you can leave it as a decimal or make it into a fraction. If you have an unpleasant decimal, you should make it into a fraction. Okay, so 32 times 2.5 gave me 80. 80 times 2.5 does give me 200. Then multiply that by 2.5 again, and that does give me 500. So that tells me I did have the right multiplier. My function is my starting value times my multiplier to the power x. So when we're given a table like this, writing down the function is just a matter of finding the starting value and then finding the multiplier. In these next few examples, we're not given the full table. The table is only partially filled in. In table A, though, we still have our starting value that was given to us. So that's our number A. And then looking at the pattern, I don't necessarily need my calculator for this one, right? I can see every time I go down a row, I multiply by 2. And so continuing this pattern, in that last space, I'll have 32 times another 2 is 64. And my function, I'll have my starting value, 4. Oh, I wasn't given the y equals this time, right? So I'll have to say y equals my starting value, 4, times my multiplier, 2, to the power x. So there's my exponential function. On this next table, again, I'm given my starting value, a. To figure out my multiplier, I think I might need to do division. Right, I'm going to take 54 divided by 162. So just second row divided by first row. Oh, and I see that that gave me a repeating decimal, so I am going to convert that one into a fraction. Okay, every time I go down a row, I'm multiplying by 1/3. Right, I should confirm 54 times 1/3 gives me 18. Okay, so that works. And then if I continue, multiply by 1/3 again. I get 6. And then one more time, I get 2. So the next two rows in the table are going to have a 6 and a 2. My equation is y equals my starting value of 162 multiplied by 1/3 to the power x. Okay, Now we've got weird things happening. Because in this next table, we're not given the value of A. We're not given the starting value in the first row. But we know that every time we go down a row, we have to multiply by the same thing. So instead of taking the second row divided by the first, we can take the third row divided by the second. Gives us 3. Every time we go down a row, we should be multiplying by 3. So we can keep going down, right? 27 times 3 is 81. Times 3 again is 243. But what about if we want to go up a row? If we want to go up a row, well, we have to do the opposite of multiplying by 3. We have to divide by 3. So we'll take 9 divided by 3, which is 3. So we can figure out our starting value. We just need to be able to go up a row in our table. That gives us the equation y equals, our starting value we found is 3, times, oh, in this case it happens that our multiplier is also 3. So 3 times 3 to the x. So that first 3 is just used once, and then the second 3 is used x times. Okay, this next one is a little bit weirder still. Because here we're skipping down 2 rows. So going down these 2 rows, we multiplied by 4. We can see that pretty easily. But multiplying by 4 is just what we got when we multiplied by our unknown thing twice. What is it that when we multiply it by itself, we get 4? Well, we can use a little trial and error, right? 1 times 1, that's not 4. 2 times 2, oh, that's 4. Right? 2 times 2 is 4. So every time we go down a row, we're multiplying by 2. 100 times 2 is 200. 200 times another 2 is 400. Times another 2 will give us 800. And then if we'd like to go up a row, we'll need to divide by 2. So here our number A, our starting value, is 50. So here our equation is y equals our starting value of 50 times every time we go down a row, we multiply by 2, and that's raised to the x power. I feel like I want to check that, right? I'm going to take 50 times 2 to the 4th power and confirm, yeah, I really do get that 800 that I see when my x is 4. Okay, so let's see a couple more applications of these exponential patterns. So suppose we've got a rabbit farm, and on our rabbit farm, our rabbits are reproducing exponentially. But we don't know at what rate, right? We don't automatically know what the multiplier is. So we look around our farm when it's been open for 2 months, and we notice that we have 18 rabbits. And then later on, when we've been open for 4 months, we notice that we have 162 rabbits. So our first order of business here is to figure out what the multiplier is. So first we'll take 162 divided by 18. This is just like example D from before. So in going down these 2 rows, we multiplied by 9. But that means we've multiplied by our multiplier twice. Our multiplier is the number that when we multiply by it twice, we get 9. So let's use some trial and error, right? 2 times 2, that was too small, that was 4. 3 times 3, there we go, that's 9. So every time we go down a row in this table, we want to be multiplying by 3. So we'll take 18 times 3 is 54. Times another 3 is 162. Times another 3 is 486. And then just like in the earlier examples, if we want to go up a row instead, we have to divide by 3. So 18 divided by 3. So at the 1 month mark, we had 6 rabbits. At the 0 month mark, when we opened our rabbit farm, we had 2 rabbits. Fortunately, we are mathematicians, not biologists, so we will not have any conversations about genetic diversity. So our multiplier, B, every time we go down a row, our output is multiplied by 3. That means every time a month passes, the number of rabbits multiplies by 3. Multiplies by 3, there happens to be a specific word for that. The number of rabbits triples. Looking at the table again, the output, when the input is 0, input is 0, output is 2. That's our number A. And that means when we first opened the rabbit farm, so after 0 months, when we first opened the farm, we had 2 rabbits. Okay. So our exponential equation, our output is called n, so we'll say n equals, our starting amount is 2, and then our multiplier is 3. So n is 2 times 3 to the x power. This last question asks us to find the number of rabbits. So what is n? After 8 months. So when t is 8. We'll plug that into our equation. We'll leave n 2 times 3 to the 8th power. This is a job for a calculator. 8th power is a job for a calculator always. 2 times 3 to the 8th. We get 13,122. So after 8 months, there are a lot of rabbits, 13,122 rabbits. And I think that gets an exclamation point because that's a lot of rabbits. This is kind of the function of exponential growth, right? As time goes on, exponential growth gets just faster and faster and faster. Let's see one last example of an exponential model. So Bill right now has $25 in savings. He makes a plan where he's going to save enough money so that every month from now on, he'll have 1.2 times as much, or excuse me, every week from now on, he'll have 1.2 times as much as he did the week before. So right now he has $25. And every month, every week, he plans to multiply his savings by 1.2. So that means, so he starts with $25, multiply that by 1.2. He wants to save money so that next week he'll have $30. We can see how he's going to do that, right? He's going to put an extra $5 in. Multiply by 1.2 again. The week after that, he wants to have $36. Do that again. This is money, so I'm going to say $43.20. Again, then I have $51.84. And one more time. This is money, so I'm going to round to 2 decimal places. At 5 weeks, he's going to have $62.21. Our multiplier was something we were told. That was 1.2. That's the each week. He has 1.2 times what he had before. And the starting value A was 25. Again, that was given. He starts with $25. So his savings is equal to his starting $25 times 1.2 to the power t. And then this last question, we're asked, how much will Bill have saved? That's asking, what is the value of S in 18 weeks when t equals 1.2, if he follows the same pattern. So if we keep doing this until, sorry, not t equals 1.2, until t equals 18, right? So after 18 weeks. So we plug that into our equation, and we have S equals 25 times 1.2 to the 18th power, 25 times 1.2 to the 18th power. And again, this is money, so we're going to round to 2 decimal places. So 665.58. He has $665.58 after 18 weeks. So that's exponential models. We identify the starting value, we identify the multiplier, and that gives us our exponential equation.